The conditions necessary for the existence of life, at least in our understanding, are very specific and complex. First, liquid water is often considered the primary solvent for biochemical reactions. Water facilitates the transport of nutrients and waste, helps regulate temperature, and plays a key role in cellular processes. That's why the search for extraterrestrial life often begins by looking for water in places like Mars or the icy satellites of Jupiter and Saturn. Second, a stable source of energy is required. For life on Earth, the sun is the primary source of energy, providing photosynthesis for plants and regulating climate. However, other potential energy sources, such as geothermal sources on the ocean floor or chemical reactions, can also support life. Energy must be available in a form that organisms can convert into biochemical processes to sustain their life. Another important prerequisite is the presence of basic chemical elements, often referred to as the basis of life. These include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon is a special element that can form complex and strong bonds with many other elements that form the basis of organic molecules, such as proteins, lipids, nucleic acids, and carbohydrates. In addition, a favorable environment with moderate temperature and air is extremely important. Changes in temperature can denature proteins and nucleic acids, while a stable atmosphere provides protection from harmful radiation and facilitates the exchange of gases, such as oxygen and carbon dioxide, necessary for respiration and photosynthesis. Finally, time is an often overlooked but very important factor. Life, especially difficult life, does not happen overnight. Evolution from simple molecular interactions to the development of complex multicellular organisms requires long periods of time. This process can take billions of years and depends on the stability of the planet over time, including factors such as tectonics, magnetic fields, and the absence of cataclysms. The conditions necessary for life to flourish include a delicate balance of available liquid water, energy sources, essential chemical elements, a favorable environment, and sufficient time for evolutionary processes. These criteria lay the foundation for natural processes that may one day produce life, whether on Earth or perhaps on distant planets. Extremophiles, organisms that thrive in extreme conditions on Earth, offer a fascinating window into the possibilities of alien life. These resilient life forms can tolerate conditions previously considered absolutely harsh. For example, thermophiles can survive in boiling hot springs, while cyclophiles thrive in the icy waters of the Arctic and Antarctic. Acidophiles thrive in very acidic environments, such as sulfur hot springs, and halophiles thrive in extremely salty environments, such as salt marshes and salt ponds. These creatures challenge our understanding of the limits of life by expanding the range of environments in which we might expect to find extraterrestrial life. Take, for example, water bears, also known as silent bears. These tiny, nearly indestructible creatures can tolerate the vacuum and radiation of outer space, extreme temperatures, and high pressures. Their resilience suggests that life, if it exists elsewhere, may not be confined to Earth-like conditions. Another remarkable example is the discovery of microbial life many kilometers below the Earth's surface in rock formations, suggesting that life may exist in similar subsurface environments on other planets or moons. Thus, the study of extremophiles contributes to the search for life on other planets and moons. The icy moons Europa and Enceladus, which have subsurface oceans beneath their frozen crust, are prime candidates for life. The presence of hydrothermal vents on the ocean floor could provide them with the heat and minerals they need. They are very similar to vents on Earth where extremists thrive. Mars, with its traces of former liquid water and modern underground ice, is another target, especially in the perchlorate zones where cytophiles are likely to survive. By studying extremophiles, scientists will be better able to develop missions and instruments to detect life in extreme environments beyond Earth. For example, NASA's Mars rover, Persistence on Mars, aims to collect samples that may contain signs of ancient microbial life and look for them in places similar to Earth's hydrothermal environment. The devices are designed to detect specific biosignatures based on what we know about extremophiles. Extremophiles serve as ambassadors for Earth in an effort to understand the potential for life beyond our planet. They demonstrate that life can adapt to a multitude of extreme conditions, expanding the horizons of astrobiology and offering valuable insights into where and how we might find signs of life in other parts of space. Detecting life on other planets involves identifying key indicators or biosignatures that point to biological activity. The focus is on looking for chemical, physical, and sometimes geologic markers that directly or indirectly indicate the presence of life. These range from the composition of a planet's atmosphere to surface features that can be detected by telescopes and space missions. One of the most important biosignatures is the presence of certain gases in a planet's atmosphere, often associated with biological processes. For example, oxygen is a strong indicator because it is highly reactive and quickly depleted if it is not constantly replenished. On Earth, this occurs through photosynthesis. Methane is another important gas because microorganisms can produce it. Oxygen and methane found together can be particularly telling because they react with each other, depleting each other's concentration and replenishing to a lesser extent certain processes, suggesting that a balancing movement may be maintained by life. Another important sign is the presence of liquid water. As a universal solvent, water facilitates most known biochemical reactions. Many missions, such as the Mars rover or the Europa lander, are aimed at finding signs of liquid water or its presence in the past. Features such as river valleys, lake beds, or spectral signatures of hydrated minerals reveal the history of water and its life potential. Surface features and geologic formations also play an important role. For example, stromatolites, layered structures created by microbial communities on Earth, provide direct evidence for the existence of microbial life. The discovery of similar structures on other planets or moons may indicate similar life forms. Telescopic observations also scrutinize changes in the reflectance spectrum of the planet's surface that indicate vegetation or other biological activity. Organic molecules, complex carbon-based compounds, are another promising indicator. Landing vehicles such as the Curiosity rover have found intriguing signs of complex organic molecules in Martian soil. Although not definitive proof, the presence of these compounds may indicate prebiotic chemistry or even active biological processes. Another interesting aspect concerns technological signatures or signs of advanced technological civilizations. These include unusual light patterns that may indicate man-made structures or waste heat detected by infrared telescopes, indicating large-scale energy consumption. Radio signals or other forms of communication may also be signs that initiatives such as SETI, Search for Extraterrestrial Intelligence, seek to detect. Key indicators of life on other planets include a range of evidence, from specific atmospheric gases and liquid water to geologic formations and organic molecules. Each of these signatures helps provide compelling evidence for the potential presence of life, shaping the design and focus of space missions as humanity continues the search to find out if we are alone in the universe. The search for biosignatures on exoplanets is a multifaceted endeavor that relies on advanced technology, sophisticated techniques, and a deep understanding of both astrophysics and biology. The primary tools for these searches are powerful telescopes, both ground-based and space-based, equipped with sophisticated instruments capable of analyzing light from distant celestial objects. Using a combination of techniques such as spectroscopy, direct imaging, and transit observations, scientists seek to detect signs that may indicate the presence of life. Spectroscopy is one of the most important techniques used in this study. When a planet passes in front of its parent star, starlight is filtered through the planet's atmosphere, and molecules in the atmosphere absorb light wavelengths of specific wavelengths. By studying the resulting spectra, scientists will be able to determine the chemical composition of the atmosphere. For example, the James Webb Space Telescope, JWST, uses infrared spectroscopy to analyze the atmospheres of exoplanets. They look for important gases, such as oxygen, methane, and water vapor, that could signal biological activity. Direct imaging, although difficult because of the vast distances and brightness of the host stars, is another method gaining momentum. Coronagraphs and star shadows are technological advances that help block out the star's light, allowing telescopes to pick up reflected light from the planet itself. Spectra obtained from reflected light can provide detailed information about a planet's atmosphere, surface conditions, and potential biosigns. Future missions, such as the proposed Large UV Optical IR Surveyor, LUVOIR, aim to use these technologies to obtain direct images of Earth-like exoplanets and their potential signs of life. Observations of transits offer another avenue. When a planet passes by its star, it causes its light to fade slightly. Analyzing these light curves helps determine the planet's size, orbit, and even signs of atmospheric conditions. Space telescopes, such as TESS, the Transiting Exoplanet Survey Satellite, and its predecessor, Kepler, have discovered thousands of exoplanets using this method. In addition, by studying how a star's light changes as it moves, scientists will be able to infer the composition of its atmosphere. Ground-based telescopes also play an important role in this hunt. Instruments such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will have sufficient resolution and light-gathering capabilities to find and analyze exoplanet atmospheres. These observatories, despite the difficulties associated with Earth's atmosphere, still provide higher resolution and the ability to make long-term observations. The combination of these methods allows us to obtain multidimensional images of exoplanets and their potential for life. The ultimate goal is to find biosignatures, compelling evidence of life processes in the form of certain atmospheric gases, surface features, or even temporal changes in a planet's environment. Each discovery or non-discovery refines our models and improves future search strategies. We are getting closer to answering the profound question of whether we are alone in the universe. The Drake equation is a probabilistic formula developed by Dr. Frank Drake in 1961 to estimate the number of active, sociable extraterrestrial civilizations in our Milky Way galaxy. While this does not provide a definitive answer, it provides a foundation for scientific research in the search for intelligent life beyond Earth. The equation breaks down a complex question into more manageable subcomponents, each of which represents a variable that can be studied, measured, or evaluated through astronomical and biological research. Drake's equation is often written as follows: Nn equals R, star times F sub P times N sub E times F sub L times F sub I times F sub C times L. In this equation, N represents the number of civilizations with which humans could communicate. Let's look at the variables. First, star R is the average rate of star formation in our galaxy. This variable is relatively well understood through astronomical observations, typically estimated at 1 to 3 stars per year. Second, Fp is the fraction of stars with planetary systems. Observations from spacecraft such as Kepler and TESS have shown that planetary systems are quite common. The vast majority of stars have planets. Third, An sub E is the average number of planets capable of supporting life per planet-bearing star. This includes Earth-type planets in the habitable zone, where conditions can allow liquid water to exist. Current estimates vary widely, but current research is continually improving this number. Fourth, F sub L is the fraction of planets on which life actually appears. This is one of the most speculative factors because it depends on our limited understanding of how life begins. Earth is our only data point, so this estimate is highly uncertain. Fifth, F sub I refers to the fraction of habitable planets on which intelligent life appears. This number remains speculative because it requires a thorough understanding of the evolutionary processes that led to the emergence of intelligence. Sixth, F sub c refers to the fraction of civilizations that have developed technology capable of sending detectable signals into space. This includes technologies such as radio telescopes and other forms of electromagnetic communication. Seventh L is the period of time over which these civilizations emit detectable signals into space. This can be influenced by many factors, including the lifespan of a civilization, technological progress, or even self-destruction. By multiplying these terms, the Drake equation provides a framework for estimating n, sparking both scientific curiosity and philosophical debate. Although the values of the variables are imprecise and controversial, the equation itself has played an important role in guiding research programs such as SETI and the search for extraterrestrial intelligence. He encourages an interdisciplinary approach that combines astronomy, biology, and even sociology to answer one of humanity's deepest questions. Are we alone in the universe? Europa, one of Jupiter's satellites, is an ideal candidate for the search for extraterrestrial life, because it is believed to harbor a vast underground ocean beneath its icy shell. Scientists have developed several missions and advanced technologies to explore this hidden ocean, to understand its composition, dynamics, and potential to support life. NASA's upcoming Europa Clipper mission, scheduled to launch in the early 2020s, is the flagship of this research. The spacecraft will conduct a detailed exploration of Europa's icy shell and the ocean beneath it using a suite of sophisticated instruments. These include ice-penetrating radar to determine ice thickness and identify subsurface lakes, spectrometers to analyze surface composition, and magnetometers to determine ocean salinity and depth by studying variations in Europa's magnetic field. High-resolution cameras will take detailed images of the surface, showing features such as ridges, cracks, and possible plumes of water vapor erupting through the ice from the ocean beneath. The possibility of water plumes rising from Europa's surface, first hinted at by the ANDAMP, Hubble ANDAMP, Space Telescope, presents an exciting opportunity for direct sampling. If the Clipper mission confirms these plumes, they could be analyzed by flying a spacecraft through them, allowing water vapor and ice particles to be collected without having to drill through the ice. Such samples may contain organic molecules or even microbial life, giving a glimpse of the moon and how habitable it is. In the longer term, ambitious proposals for land-based and even underwater vehicles are being developed. One such concept is the Europa Lander mission, which aims to descend to the surface and deploy instruments that can drill through the ice and reach the ocean beneath. The descent vehicle would be equipped with instruments to analyze the chemical composition of the ice and possible organic compounds. More futuristic ideas include cryobots, robotic probes that would work their way through the ice using heat, and underwater drones known as hydrobots to directly explore the ocean. These underwater robots could be equipped with cameras, flashlights, and sensors to navigate the dark, high-pressure environment, look for signs of life, and study ocean properties in unprecedented detail. Exploring Europa's oceans requires overcoming significant technical challenges, from dealing with the extreme levels of radiation emanating from Jupiter to ensuring that spacecraft and probes are sterile to avoid contaminating terrestrial life. Despite these challenges, the scientific community is optimistic that these missions will provide groundbreaking new insights into one of the most intriguing environments in our solar system. By combining orbital reconnaissance, plume sampling, and eventually exploring the subsurface, researchers hope to unlock the secrets of Europa's ocean and perhaps discover the first evidence of life beyond Earth. Meteorites serve as invaluable messengers from space, providing a wealth of information about the early solar system, the elements of life, and even the possibility of life elsewhere. These rocky fragments, which often originate from asteroids and sometimes from other planets and moons, can survive their fiery journey through Earth's atmosphere and fall to our planet, where they are scrutinized by scientists. One of the most important discoveries made on meteorites concerns the presence of organic molecules, which are chemical precursors to life. For example, more than 90 different amino acids were found in the Murchison meteorite that fell in Australia in 1969. Remarkably, some of these amino acids are not found on Earth, suggesting that organic chemical processes occur naturally in space. This discovery supports the hypothesis that the first ingredients of life may have been brought to Earth by meteorite impacts, which may have triggered the development of life. Meteorites also provide insight into the primordial conditions of the solar system. Analyzing the isotopic ratios in these rocks, ratios of elements such as hydrogen and carbon, helps scientists understand the processes that formed the matter of the early solar system. For example, chondrites, a class of stony meteorites, contain tiny spherical inclusions called chondrules that provide insight into conditions and processes in the solar nebula from which our solar system formed. Martian meteorites are particularly intriguing, such as ALH 84001, which was found in Antarctica in 1984. This meteorite is thought to have been ejected from the surface of Mars by an asteroid impact and traveled through space before falling to Earth. Inside ALH 84001, scientists found tiny carbonate globules that some researchers initially interpreted as fossilized evidence of Martian microbial life. Although this interpretation remains controversial, the meteorite has nevertheless shown the presence of liquid water on Mars in the past and has generated considerable interest in Mars as a habitable environment. Isotopic analysis of meteorites also helps trace the history of water in our solar system. For example, some meteorites contain minerals that indicate there was once water inside them. By studying these hydrated minerals, scientists are gaining insight into the distribution and history of water in the early solar system. This has implications not only for understanding the sources of water on Earth, but also for assessing the habitability of other celestial bodies. The meteorites have greatly enriched our understanding of the possibilities of life in space and the early history of the solar system. They reveal the presence of organic molecules and provide evidence of chemical processes that may have led to the origin of life. They also provide insight into the history of water in space and the possible habitable past of planets such as Mars. Thanks to these extraterrestrial rocks, we continue to piece together the puzzle of the origin and distribution of life in space. Exploring the potential for life on Mars is a complex and interdisciplinary endeavor that involves a combination of robotic missions, remote sensing technologies, and laboratory research on Earth. Scientists seek to understand the past and present of Mars, looking for signs of water, organic molecules, and other conditions favorable to life. Robotic missions are at the forefront of this research. NASA's Mars rovers, such as Spirit, Opportunity, Curiosity, and the recently landed Perseverance, are equipped with many sophisticated instruments designed to explore the Martian surface. Spirit and Opportunity have uncovered evidence of ancient water flows, finding minerals and geologic formations formed in the presence of water. Curiosity landed in Gale Crater in 2012, analyzed rock samples and found organic molecules, complex carbon-based compounds essential for life. Evidence has also been found that Gale Crater once contained a lake with conditions that may have been suitable for microbial life. Perseverance takes these explorations to the next level. Equipped with advanced scientific instruments, including Sherlock, which scans habitable environments using Raman light scattering,
and luminescence for organics and chemicals, and PXL, a planetary X-ray lithochemistry instrument. Perseverance searches for biosignatures and drills core samples of Martian rocks. These samples are being stored for a future mission to return to Earth, where they can be analyzed in state-of-the-art laboratories, possibly providing definitive evidence of life in the past. Remote sensing technology also plays an important role. Orbiters such as NASA's Mars Reconnaissance Orbiter, MRO, and the European Space Agency's Mars Express use high-resolution cameras and spectrometers to analyze the planet's surface and atmosphere from above. These orbiters can identify mineral deposits, map ice distribution, and even detect subsurface water using radar. Observations from these spacecraft are helping scientists identify promising landing sites for future missions and provide a broader context for the conclusions drawn by surface rovers. Another intriguing area of research is seasonal methane emissions on Mars. Methane can be formed by geologic processes, but on Earth, a significant amount of methane is produced biologically. The periodic detection of methane in Mars's atmosphere, observed by the instruments of the Curiosity rover and Trace Gas Orbiter, raises the question of the possibility of microbial life on Mars, although non-biological explanations remain possible and are being actively explored. Laboratory research on Earth complements these efforts. Scientists study Martian-like environments, which are places on Earth that mimic Martian conditions, such as the Atacama Desert in Chile or the arid valleys of Antarctica. This research is helping scientists understand how life can survive in harsh environments and develop methods for detecting life that can be applied to Mars. Researchers are also conducting experiments that simulate environmental conditions on Mars to test the survival and adaptability of microorganisms. The search for life on Mars is a multifaceted effort involving robotic explorers, orbiters, laboratory modeling, and interdisciplinary scientific research. By collecting data from ground-based missions, orbital observations, and Earth-based studies, scientists are piecing together the history of Mars's climate and geology, looking for chemical evidence of life, and laying the groundwork for future studies that will answer the question of whether life ever existed on the Red Planet.
The discovery of phosphine on Venus has caused considerable excitement and debate in the scientific community because it suggests the possibility of life or unknown geochemical processes in its atmosphere. Phosphine, pH3, is a molecule composed of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is produced by industrial processes or in anaerobic oxygen-free ecosystems, including microbial activity. The discovery of life on Venus is intriguing because it raises questions about the possibility of biological or chemical processes there that have not yet been studied. The discovery was made with the James Clerk Maxwell Telescope, JCMT, in Hawaii and confirmed by the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. These instruments detected a spectral signature consistent with phosphine in Venus's clouds, where temperatures are relatively moderate compared to the scalding surface below. The concentrations detected were much higher than can be explained by known abiotic processes such as volcanic activity, lightning, or reactions involving sunlight and minerals. The significance of this discovery lies primarily in the context of astrobiology and planetology. Phosphine is a potential biosignature gas because on Earth, its production is largely associated with life processes. If the phosphine on Venus is indeed of biological origin, it would mean that microbial life exists in the planet's temperate but very acidic clouds, challenging our ideas of where life might evolve. Caution is required, however. The discovery of phosphine does not necessarily mean that life exists on Venus. There are many unknowns and complex questions in the field of Venusian chemistry. This discovery has led scientists to propose alternative abiotic mechanisms that could explain the presence of phosphine. For example, the extreme conditions of Venus's atmosphere can produce strange chemical reactions that we still don't understand. Further observations and missions are needed to build on this discovery. Upcoming missions include NASA Veritas, Venus Radiation, Radioscience, INSAR, Topography and Spectroscopy, the Venus and Visualize. Missions are planned to analyze the atmosphere and geological characteristics of Venus in more detail. These missions could help determine whether the phosphine detected is a byproduct of unknown abiotic processes or a potential sign of life. The discovery of phosphine on Venus is significant because it opens new avenues for research in both planetology and the search for extraterrestrial life. It challenges our current understanding of atmospheric chemistry and emphasizes the need for further study of Venus's atmosphere to determine the true nature of this enigmatic molecule. The findings have renewed interest in Venus, often overshadowed by Mars, as a candidate for answering one of humanity's deepest questions: are we alone in the universe? When scientists categorize exoplanets in terms of habitability, they often look at a number of factors that determine whether these distant worlds could potentially support life. First and foremost is the concept of the habitable zone, often referred to as the undamp, Goldilocks zone and damp, This is the region around the star where the temperature is optimal, neither too hot nor too cold, for liquid water to exist on the planet's surface. Liquid water is considered essential to the existence of life as we know it. For example, a planet too close to its star may experience extreme temperatures that cause water on the surface to boil off, while a planet too distant may be so cold that water remains perpetually frozen. Beyond the habitable zone, scientists also look at factors such as atmosphere, planet size, and composition. A dense atmosphere rich in greenhouse gases such as carbon dioxide can trap heat and support liquid water, even if the planet is on the colder edge of the habitable zone.
Conversely, an atmosphere that is too thin will not be able to maintain stable conditions on the surface. The size of the planet is also important. Planets that are too small may not have enough gravity to hold an atmosphere, and planets that are too large may become gas giants with harsh environments. In addition, the presence of elements such as oxygen and nitrogen in the atmosphere can indicate chemical processes potentially beneficial to life. Thanks to advances in technology, including space telescopes and spectrometers, scientists continue to refine these criteria, making the exciting search for habitable exoplanets even more exciting and hopeful.